Hello Gary, and thank you for your video response. This will be my response to your video. Let's start again with what Newton was actually saying, because I think I realized something quite interesting when I was reading his second law and also some other parts of Principia. So, based on this text here and maybe some other parts, I think the safest assumption is that the alteration of motion here means the change in momentum. Not the rate of change in momentum, but the total change in momentum. Whereas the conventional definition is about the rate of change in momentum. So there is a difference. You have been correct about Newton. I was incorrect in my previous video. So the difference in these definitions is how they relate to time. The Newton's definition describes a change in the system over some period of time, whereas the conventional definition describes the system at some point in time. Here we can use a bucket analogy, so buckets collecting rainwater. Conventional definition would be about how fast the bucket is filling up at some point in time, or how heavy is the rain at some point in time. And often that is described as volume per time. And you can make this time as short as you want. So basically you can talk about a point in time. And Newton's definition would be how much water was collected during some time, so that would be just volume. So the difference is how these definitions relate to time, and Newton's force is what conventional force accumulates into over some period of time. Okay. I have to admit that I was quite surprised when I realized this, and I think this is quite disturbing from the point of view of science education and history of science. But unfortunately, I don't think that this solves any of our problems, because it's just about definitions, about name tags that we want to give to different things. So let's talk about the arguments itself, or arguments themselves. So in your response video, you were talking about springs and momentums and how I can't explain why springs wouldn't conserve momentum, or how springs would tell any difference between equal momentums. So here's a thought experiment about that. At least according to my understanding, your claim has been that equal momentums cause equal spring compressions. And I would argue that that just can't be true. That can't happen. If we assume this, then we are going to run into contradictions, or at least have some very difficult things to explain. So let's first note that when we are talking about spring compression, we can talk about either the length of the compression, meaning how many inches or centimeters we are making the spring shorter, or we can talk about the duration of the compression, meaning how long the spring feels the weight. Here we have two identical springs, two objects with different masses and velocities but equal momentums. They hit the springs and compress them. And if we assume that the length of the compression is the same, we have to conclude that this faster object does everything faster. It compresses the spring faster, releases the spring faster. So it applies the weight for a shorter period of time, meaning that this other spring here for some time would feel additional weight. So where does that come from? How would you explain that in terms of momentum alone? Or conversely, we can assume that the duration of the compression is the same, but then we must conclude that the length of the compression must be longer for the faster object. I think that this clearly shows that springs can tell a difference between equal momentums, and especially it shows that you really need something in addition to momentum. if you want to explain these things. Momentum alone isn't enough. It just isn't enough. Okay. Here's a similar example dealing with much of the same thing. So we have equal balls here with masses of 10. Then we have a small object and a large object. And compressed springs, we will release the springs, let them push these objects into opposite directions. And just for the sake of the argument, let's make two assumptions. The first is that both springs create equal amounts of total momentum. And the second one is that each spring creates equal momentums to both directions. Based on these assumptions, we can conclude that the 10 mass balls will gain equal velocities. So obviously they will gain equal momentums, and since they have equal masses, they will gain equal velocities. And does this make sense to you? Does this seem reasonable? That these balls here with identical springs would gain equal velocities. Even though this ball here is pushing against a tiny object and this other one is pushing against a large object. I don't think that you believe this to be the case. So at least one of our assumptions must be incorrect. Which one? I would say that assumption number 2 must be correct. I think that springs always create equal momentums to both directions. So in that sense they are balanced. Meaning that assumption number 1 must be incorrect. Identical springs don't always create equal amounts of total momentum. It depends on the objects that the springs are pushing. But again, I think this shows that momentum alone is not enough. You need something else. Then one more thought experiment. This is basically the same as the gun and the bullet in the previous video. There I was trying to make a point that I thought was quite important, but I felt like you didn't quite understand that. So here I try to make it in a more clear fashion. So again, here we have a heavy object, a light object, compressed spring. We will release the spring will push both of these objects. And obviously the lighter object will travel further distance within some unit of time. Let's also decompress the spring like this. And again, I would argue that it's quite easy to see that most of the length of the spring was traveling to the direction of the lighter object. And a smaller part of the spring was traveling to the direction of the heavy object. And based on this, we can conclude that there must be this kind of division line, that on the other side of the line, all the spring was traveling to the direction of the lighter object, and on the other side, all the spring was traveling to the direction of the heavy object. So basically there's a point in the spring that wasn't moving into any of these directions. Which means that we can basically imagine an immovable wall here. Because nothing was moving here where the wall is. So we can just imagine an immovable wall here. And now we can also see that we basically have two springs on both sides of the wall. One long spring and one shorter spring. And the lighter object, which gains higher kinetic energy, was pushed by the longer spring. Makes sense, right? And again, if we rewind this scenario, so we make the objects approach each other and also compress the spring, we can see that the lighter object with higher kinetic energy was able to do more compression work. It was able to compress the longer spring in comparison to the heavy object. So this was the point I was trying to make. But yeah, I think that I made here quite strong points on that momentum alone just isn't enough. explaining how springs work. You need something else. And based on this last experiment here, I would say that kinetic energy makes pretty good sense. Okay, that was it. Bye.